All right. Yep. So this is the fourth lecture in these atomic structures and electronic configurations. We are going to talk today about the Schrodinger equation and how to solve it in a one-dimensional space. And then we'll talk about what the solutions look like in a three-dimensional space for the hydrogen atom. And eventually we're going to have the wave functions and the orbital shapes for a hydrogen atom. And we're going to talk about the energy states of a hydrogen atom and an individual and a silicon atom. Okay? There's a few concepts that we're going to do today as well so that you understand what the Schrodinger equation is all about. We started building up to this last class. In this class, what we're going to do is solve the Schrodinger equation for a few simple one-dimensional problems to give you an idea of how these wave functions work. And also, I'm actually going to go through a derivation of the one-dimensional Schrodinger wave equation also, so you can have a deeper understanding of how the equation is derived and how it works, and some of the intuitions that Schrodinger himself probably had when he came up with this equation. All right. I don't do this in the undergraduate version of this class because we don't have time, and most of the semester is just covering the basics of the three types of devices, the diodes and MOSFETs and so forth. But in this class, I want to go a little bit more in depth. Okay, so let's quickly review what we did last time so you have a context. When we started talking about finding the locations of the electrons, the reason we're interested in finding the locations of the electrons is because that tells us about the electronic behavior of the material. All right, and what we see is that at this size scale, particles are governed by a wave-like behavior, not just particle-like behavior. Okay, the concept of wave-particle duality we covered in last class. So the key concept in wave-particle duality boiled down to de Broglie's equation. De Broglie said that if a particle is moving at a certain velocity, so you have a particle with a certain mass that's moving at a certain velocity, it's going to have an equivalent wavelength. Okay, and this brings together the concept of particle and wave-like behavior in a deceptively simple equation that's turned out to be correct. One part of that we found is that the wave number is just a notation that we often use. The notation for K is a wave number, and that is another way to describe the wavelength. The wavelength and wave number are inversely related. And so the wave number is equal to h times k. The momentum is equal to h times k. That's going to be important when we derive the Schrodinger's wave equation. All right, and this h with the little bar across it is just the Planck's constant divided by 2 pi. All right, so that was the concept of excuse me, of the wave-particle duality. Now, we also talked about the Heisenberg uncertainty principle that basically said that you can't measure the position of an electron with complete certainty. And as a result of that, we started talking about probability distribution functions, PDFs. We talked about an example of a uniform and non-uniform probability density function. Okay, what does a probability density function tell us about an electron? The probability that it'll be located in a space. And how do you calculate that probability? Do you just look up the value of the function? There's something you have to do to the function to calculate the actual probability. You have to integrate it over a space. If we're talking about a one-dimensional problem, you integrate it over dx. If you're talking about a two-dimensional space, a dx dy. And if you're talking about a three-dimensional space, which is what the real world is, then you have to integrate over dx, dy, dz. And you're not limited to Cartesian coordinates either. You could do it in spherical coordinates as well. Okay, so we talked about uniform and non-uniform probability density functions. This was an example of where the electron is more likely to be between 1 and 3. This is a case where the electron can be, there's equal probability of it being anywhere. All right, with the probability density functions, we found that if we integrate over the entire space, the integral of that, the probability density function is equal to 1. Now, one subtle note but important note about the psi function is a wave function. In order to find the probability density, you have to take the absolute value of that function and square it. That's just a rule of the wave function. So we talked about wave functions and wave packets last time. It indicates the behavior of a wave-like particle. Wherever psi is large, there's a high chance of finding the electron there. But if you want to calculate the actual probability, you have to use psi, absolute value of psi squared, which is psi times its complex conjugate, because psi is a complex valued function.
But why do we have like it's already going to be squared, so why do we get the absolute value? So when it gets squared, so it's going to be like a positive anyway.
Well, the psi can have a negative value as well. You know, as you can see in this example. Yeah, go ahead.
Yeah, but when you square it, it's going to be positive.
Correct.
So
correct.
The absolute value with the square together we don't need both.
Well, the reason the absolute value, the question is, why do you need this absolute value sign? Yeah. So when you take a number and its complex conjugate, you get the absolute value squared. So if you take a plus, here. So if you have a complex number, oh, why is it showing that? Oops. A plus I times b. So this is a complex number, a plus I times b, and then the complex conjugate is a minus I times b. All right, if you multiply these two together, you get a squared minus I squared b squared. And so this is equal to the absolute value of that psi function squared, the magnitude of that squared. So the magnitude of, if this is a complex number, this is the complex conjugate. So let's say psi is equal to this, psi star equals this. So if you multiply the two together, you get a squared minus I squared times b squared. So this is equal to a squared plus b squared. Okay, so this is psi times psi star. And remember, if this is a complex number, on the complex plane, this is the real part, and then this is the imaginary part. So this is a plus I times b. And so the magnitude here is equal to the square root of a squared plus b squared. This is a, and this is b. And this here is the square root of a squared plus b squared. So this is the magnitude of psi. Right? It's the square root of a squared plus b squared. And if you square this, so the magnitude of psi squared is equal to a squared plus b squared. That make sense? So it's just the property of complex numbers there. All right, there's this rule too, the psi and its spatial derivative are both continuous. So we're gonna that's gonna become important in some of the problems that we do today. I won't get into wave packets again this time because we spent a lot of time talking about it last time. Okay, so getting to the Schrodinger equation. So the Schrodinger equation is a quantum mechanical law describing the energy of an electron. If you're given a potential field V, it allows you to find the wave function psi. And we've been talking a lot about the wave function for the past last class. We talked about what the wave function is, how it could describe the location of an electron. Now we're actually going to find out how to calculate the wave function for a certain set of conditions. And the conditions could be as simple as an electron in free space, right? An electron in free space where the potential energy everywhere is 0. You can figure out the wave function for that. You can also figure out the wave function for the case of a single atom where you have a nucleus, and the nucleus gives off a potential field and the electron's near it. So the electron has a certain wave function associated with that. All right, so the basic idea of the Schrodinger equation, this is a picture of Schrodinger, by the way. It's on the Nobel Prize website. It's a statement of kinetic energy plus potential energy is equal to the total energy. Just like before when we talked about these, the classical mechanics up here. Here we talked about kinetic and potential energy, gravitational potential energy, electrical potential energy, a tennis ball accelerating due to gravity, a charged particle accelerating due to an electric field. In both cases, at any point in time, the total energy of that particle is equal to the kinetic energy plus the potential energy. E is equal to K plus U. So we're getting back to that concept here. And what Schrodinger did is that he tied this basic statement of conservation of energy into a wave form, a wave-like form, using de Broglie's connection between the particle and wave-like behavior. So that was Schrodinger's big contribution to quantum mechanics. From a high level, this is what happens. Like the kinetic energy is equal to the momentum squared divided by 2m. I'll show you how to get this. The potential energy, it has to do with the voltage that's applied to the system, right? If you have a charged particle, you can move it by placing it in an electric field, so that represents potential energy. And then the total energy. So this would be the total energy of the electron is equal to the kinetic plus the potential energy. If you take this equation and apply quantum mechanical operators, this is if you're really savvy with math, and this is what they talk about in our textbook, you get this three-dimensional form, a quantum form of the Schrodinger equation. And what it is, it's a, let's see if we can recognize it. What type of a differential equation is this?
Second order.
Okay, it's second order, that's right.
Partial.
It's a partial differential equation. Why is it a partial differential equation?
Because of the delta.
Yeah, the gradient operator, that's right. So this partial differential equation has derivatives with respect to time. It also has derivatives with respect to space, right? And this is the most general form of the equation. So it has it gives you a gradient operator. So del squared is called the Laplacian operator, if you remember this from calculus or from electromagnetics. So the Laplacian operator del squared of psi is equal to the second derivative with respect to x of psi plus the second derivative with respect to y plus the second derivative with respect to z. So it's kind of like it's the gradient of the gradient. All right. What does the gradient mean in one dimension, by the way?
Slope.
The slope. Right. Right. In one dimension, the gradient is just the slope. In two dimensions, the gradient has a magnitude and a direction. What does a magnitude tell you? Same thing. Slope. What does the direction tell you? Gradient vector.
The plane?
Nope, not quite. It tells you the direction to go for the maximum increase. So if I'm walking in on mountains, right, on a sloped area, the direction of the gradient vector is going to tell me which direction should I go to get the maximum, where I'll have the maximum incline, maximum slope. That's what the direction tells me, and the magnitude tells me what is the actual slope in that direction. Right, And in 3 dimensions, it's similar. Like it tells you the gradient vector in the 3 dimensions. It tells you the direction to go, which direction you go in a 3-dimensional space to get the maximum increase in this function psi. All right. And the magnitude would be how much increase you get if you go in that direction. So this is the gradient of the gradient. So it's a Laplacian, and this is the electrostatic potential times the function psi, and then you have this time derivative on the right side of the equation. So actually, we're not going to be dealing too much with this part of the equation in this class, okay? Because we're dealing a lot with steady state type events. We're trying to find at rest, in equilibrium, what do the electronic configurations of silicon look like? All right, what do the electronic configurations of hydrogen look like? So we're not interested right now in how it changes with time. So we're just going to make for a lot of the cases that we're going to look at, this is going to be 0. Let's just emphasize that again with the simpler forms of the Schrodinger equation. Now keep in mind, when we're solving the Schrodinger equation, we don't solve this equation by hand usually. All right, analytical solutions for this equation are they only happen in the most simplest of cases, and some of those simple cases we're going to look at today. Normally, this 3-dimensional time-dependent Schrodinger equation is solved using partial differential equation solvers like MATLAB, COMSOL, things like that. Or there are a lot of solvers specifically for the Schrodinger wave equation. A lot of software is available for that. We happen to have one of those softwares, COMSOL, that's just a general partial differential equation solver. So that's one way, if you're interested in doing that, that's one way you could go about it. So this is the Schrodinger equation. It's just repeated from last slide. And one simplification you can do, and this is what we're going to do for the purposes of this class, is we're going to take it down from 3 dimensions into 1 dimension. All right, so this thing here, this gradient, which is shown here, del squared times psi is equal to this here. So this is the definition of the gradient, or the Laplacian, the gradient of the gradient. So in a single dimension, this term is going to go away, this term is going to go away, because the function is, it's not a function of y, it's not a function of z anymore, it's just a function of x. All right, so as a result, that simplifies. Computer's being kind of slow right now. Okay, so as a result of that, we get the 1-dimensional time-dependent Schrodinger wave equation. And let's make this bigger. So you notice what happened here. This term, this del squared term, turned into just this. D squared psi of xt over dx squared. Everything else basically stayed the same. Wherever we have the size, it changes from psi. We just specify that psi of x and t. All right, so this v of x stayed the same. This h over j stayed the same. So d psi dt, now it becomes d psi of just x and t dt. All right, so now it's starting to get into a form where we can use it, or it becomes a little bit easier to use. But we're going to make one more simplification. We are going to make it time independent. All right, so that, like you do in when you're doing DC versus AC circuits, transient analysis versus DC analysis. In DC analysis, you make all the time derivatives 0, right? Nothing changes with time. So everything with d dt goes to 0. So when we go to the time independent form, we say all time derivatives of 0. And then there's another technique which we're not going to get into, is you can use something called the separation of variables to separate out this wave function, which is a function of x and t. You make an assumption that this can be expressed as the product of a function of x, psi of x, and a different function of t. All right. This is a technique that may be familiar to you if you took an advanced class in differential equations. Have any of you familiar with the concept of separation of variables from differential equations? A couple of you. Great. So that's what we're doing here. All right. So when we do that, notice that the time derivative here on the right side, it went to 0. So that's why we get a 0 on the right-hand side here. And wherever we had psi of x, comma t, that became psi of x. And this term here, basically, this just also became a psi of x. And we also did some mathematical simplification, this h squared over 2m. We multiplied this entire equation by the inverse of that. So that's why you get the inverse of that here, 2m divided by h squared here. And this term here just became a constant. And that constant shows up here. Okay, so this is the one-dimensional time-independent Schrodinger wave equation. So this is the form that we're going to use in a couple of the examples that we do in class. So we're going to take another step of actually deriving this one-dimensional time-independent Schrodinger equation from the basic principles. And the reason we're going to do this is because it's going to provide some good intuition on wave-particle duality and just how Schrodinger himself came up with the equation. This is not in your book, but this is something that I would like for you to know for the tests. This was in a different book called Modern Physics, which is a good book. It does a great job of explaining the Schrodinger equation and where it came from.
Do we have to derive it on an exam, or are you going to give it to us, or we can bring it in?
I don't know if I'll actually have you derive it. I just want you to understand like the concepts in the derivation. It's actually not too complicated a derivation, you'll see. All right, I've actually, to save time, I've instead of like scribbling during class, I'm just gonna, I have it written out already. I'm just gonna show you step by step and just walk you through it. The key thing I want you to get, like DeMarco's getting at, what's the important part here? I want you to understand the key intuitions here, and how to do some of the key intuition steps, the steps related to key intuitions. The first step is this: the conservation of energy has to hold true. Okay, and that's a statement of conservation of energy that I mentioned at the beginning. Kinetic energy plus potential energy is equal to total energy. So the kinetic energy of the electron plus the potential energy of the electron is equal to the total energy. So we start with a law that is rooted in classical physics. The next step, so we just say K plus U is equal to E. This is the same thing as the slide I showed you earlier when we were dealing with tennis balls and charged particles in an electric field. All right, so the first key intuition here is this kinetic plus potential energy. And let's remind ourselves what the definition of kinetic energy is. So K is equal to mv squared over 2. You know, that's from physics. And if you also remember the momentum of a moving particle, P is equal to m times v, mass times velocity, okay? So all we're doing here is we're saying K is equal to mv squared over 2, and knowing that the momentum P is equal to mv, we can just substitute that in here, all right, into this equation for K. So the kinetic energy in terms of momentum, not in terms of velocity, in terms of momentum, is P squared divided by 2m. All right. So momentum is mass times velocity. Does anyone remember what the mass of an electron is, just off the top of your head? If not, it's okay. You'll need to know it for the homework, but it's 9.1 times 10 to the negative 31 kilograms. All right. So this is just the kinetic energy of a moving particle. Quite simple. So what we do is this is what Schrodinger came up with. He's like, okay, well, the kinetic energy here, let's come up with, put something in for the kinetic energy, okay? So kinetic energy is equal to P squared over 2m. Momentum of the electron squared divided by 2 times the mass of an electron. Now at this point, we are still thinking about the system as a particle. Momentums and masses and so forth. The second of Schrodinger's intuitions was that he figured out that, okay, well, if we want to relate this in terms of a wave, this is the Schrodinger wave equation, so he's trying to take this basic relation and translate it into waveform. So you said, okay, how can we represent this as a wave? So the intuition here is that the de Broglie equation, de Broglie wave has momentum and kinetic energy. All right, so let's look at that. And this was on a previous slide. I'm just pulling it up here for you to remember. This momentum here, this momentum can be it can be due to a wave or a particle. So when we talked about the de Broglie equation, the de Broglie wavelength was equal to Planck's constant divided by the momentum. All right? And for a particle, the momentum was just equal to m times v. But now we're talking about a wave. So now what we're going to do is we're going to say, we're just going to rearrange this equation. We're going to say the momentum of a particle with the de Broglie wavelength lambda is equal to h over lambda. So we're just rephrasing this equation. The momentum of a wave with the wavelength lambda is equal to h over lambda. The wavelength here is related to the wave number k, because remember, wavelength is equal to 2 pi over k. That's the definition of the wave number. Okay, and then this h over 2 pi here is just this, we notate that as an h bar, h with a bar through it, times k. All right, so the momentum is equal to this Planck's constant over 2 pi times the wave number. Okay, this makes sense. Think about this as higher energy. Higher wave numbers corresponds to higher energy electrons. Higher energy electrons have more momentum associated with them. So you think about fast electrons have small wavelengths and large momentum. All right, so then what you do here is that you take this p squared and you convert that to a wave number. All right, so now what we've done is we've taken this equation which talks about the energy in terms of a particle form, and it translates it into a wave form. All right, now instead of talking about momentum and mass times velocity and momentum, we're talking about wave numbers. So it's h squared times k squared. All we did is we plugged in p is equal to hk here. That's all we did here. Very simple. All right, question in the back? Is there a question in the back? No? You with me so far? Okay. The third part is, and this was probably the key intuition of Schrodinger, is that the wave number of the de Broglie wave, so that k that we're talking about, can actually be related to the derivative of the wave. All right, so you can actually think about this as a mathematical trick or an intuition. Here's just to remind everyone, with sine waves, okay, just forget about wave equations for a second. Let's say you have a sinusoidal function, a times sine of kx, right? The sine function has this unique property that when you take the derivative of it, what do you get when you take the derivative of a sine?
Higher magnitude.
Well, what's the derivative of a sine function?
Cosine.
Cosine function, that's right, that's right. And what's the derivative of a cosine function? Negative sine. You see how it goes back to the sine function? That's a key property of a sine function that Schrodinger took advantage of in the mathematics here. Okay? And that happens to be a reason why sinusoidal solutions often show up in the solutions of the Schrodinger equation. That's why sinusoidal functions often show up in nature, because a lot of these physical laws are governed by differential equations which have two time derivatives, the second derivative in it. And when that is equated to the original function, then the only possible solution to that differential equation is some kind of sinusoid. And that's actually the reason why a lot of things in nature have sinusoidal equations. But anyway, let's get back to just mathematics, okay? You take the derivative of a sine wave, so the derivative of a times sine of kx is ak times cosine of kx, right? You take the derivative of that, and you get negative ak squared sine of kx. All right, because this k comes out again when you take the second derivative. When you take the derivative of cosine, you get negative sine. All right, so this is just the second derivative of a sine equation. But notice, you're getting your sine back. All right? So when you replace the sine of kx, this is the original psi of x. This original psi of x equation was a times sine of kx. All right, so hold on, I made a little mistake here. There should not be an a here. Okay, so the second derivative of the psi function is equal to negative k squared times the original psi function. And this is that unique property of sines, is that, like, you know, the second derivative is just a constant times the original function. And that's one of the tricks that's used to solve differential equations. All right, so in this case, if you take this equation and you solve for k squared, then this k squared is equal to 1 over psi of x times the second derivative of psi of x. All right, and this was the mathematical trick that Schrodinger used. He said, wherever we have this k squared, we're going to take this kinetic energy statement and make that an equation that's that has to do with the psi function and its second derivative. So this k squared is equal to 1 over psi times d squared psi over dx squared. So you just replace that in there, and you get this form here. All right, now we have an equation psi of x and the second derivative of it. So again, I like to emphasize, like, why we did certain things. Like, this was done because, okay, this equation is useful. It's telling you that the kinetic energy is proportional to the square of the wave number, but we want to actually get at the equation, the wave function itself that describes the location of an electron. So Schrodinger made the assertion that, okay, if de Broglie said that particles, and there's a wave-particle duality. So something can act as a particle, it can also act as a wave. If it's going to act as a wave, the first thing that usually comes to mind is, well, it should probably act as a sinusoid. Probably some kind of sinusoidal function should be the wave function that describes the electron. All right, that's why, you know, we start with something like this, okay, like some kind of wave function that has a sinusoidal, sinusoidal component to it. And then you use this property to relate back to the wave number k. All right, so we've taken this wave number k, and then we brought in these brought in the actual wave function, and this is the one that we want to solve for. We want to find psi of x. All right, so all we do here now is we just rearrange this equation, and it comes back to the form that we saw in the previous slide. All right, this is the more typical form of a differential equation, where you show the second derivative first, and then you show the terms that are the non-derivative terms. So this is the non-derivative term times the function. So the second derivative of this function times something times the original function equal to 0. Let me say that again. The second derivative of the function plus something times the original function is equal to 0. This is a standard form of a second order differential equation with no forcing term here. All right. So now the question is, how is the Schrodinger equation used? So go back up 2 slides. For a typical situation, we are going to be given the potential energy V. So we'll be given V. This term is going to be equal to 0. And we are going to solve for psi. And that wave function is going to tell us the location of the electron, where we're most likely to find the electron, and what the energy of the electron is. So this is the high level is this. You have, what you plug into the Schrodinger equation is a boundary condition. And that boundary condition is the electrostatic potential field. What's one way of generating a potential field that we've talked about so far? Yeah, actually doping is a way you can generate an electrostatic field. But I'm saying like what things that we've talked about just in this module.
Charging plates.
Charging plates, yeah. The simplest way of generating potential field is you take, you put a voltage between two plates, you get electric field lines, and there's your potential. When you put an electron in that potential field, then you could solve the Schrodinger equation and get the wave function for that electron. That would be an example of like where the potential is decreasing from high to low. As you go from the top plate to the bottom plate, the potential is decreasing as you go. So that's one type of potential field. Another a common type of potential field is the radially symmetric potential field, which we'll get into with the hydrogen atom. That's where you just have a nucleus. Where's the potential going to be the highest if you just have like a nucleus that's packed with protons? Yeah, the potential is going to be highest in the middle. The way that you can think about potential energy or a potential field is like if I took a positively charged particle near the nucleus. Let's say I have the nucleus is packed with protons. If I took a positively charged particle near the nucleus and I let it go, what would happen? It would accelerate. It would accelerate away, right? So the fact that I had to take that, I had to bring it close to here, right? That there's some energy stored in that system, right? When I let it go, that potential energy is converted to kinetic energy, right? So that's what we're talking about when we're talking about an electrostatic potential field. Some places there's high potential and some places there's low potential, right? In the case of that nucleus, like when the proton was close to the nucleus, there was a lot of electrostatic repulsion, potential energy. As it moves away, there's less and less potential there, right? Because it's farther away from the nucleus. If you don't have any force, there's no potential energy.
But why we previously calculate the potential energy like by multiplying the V times the charge.
Mm-hmm.
Q times the V.
Right.
Like here, the previous you just put V without the charge. Yeah.
That's a very subtle point about the Schrodinger equation, which we're not going to get into the nooks and crannies of that part of it. That's a really good question, though. It's we're making the statement here that the potential energy is U. All right. Notice I have the U in this equation, and then in the previous slide it said V of x. Right. The potential energy is supposed to be the charge times the potential, right? But with the wave function, it works a little bit differently. Okay, so that's a little bit of a detail to just, don't think too much about it. Okay, so getting back to this, so we have this boundary condition. The boundary condition goes into the Schrodinger equation. The Schrodinger equation is a differential equation, so you need to have boundary conditions to solve it. And the solution is a wave function, psi of x, y, and z. It helps describe the location of an electron. It describes the energies of the electron. And that is the electronic configuration of your system. And we're going to be looking at the electronic configuration of a hydrogen atom in this chapter, and then next chapter we will look at it for a silicon lattice. All right, so the first example that we're going to do is a free electron. This is the simplest example of the Schrodinger equation. Again, I'm just going to walk you through this step by step. You start with the boundary condition V of x equals 0. All right. Why do we do that, first of all? We need a boundary condition. In a free electron is an electron that's out here in space. There's nothing near it. All right, so there's no potential field. Okay? So what do you think that electron's going to do? I'm just curious. What does everyone think?
Is it going to look for something with lower potential?
There's no potential field. The potential is 0 everywhere.
It stays in steady state.
What's that?
It stays in steady state.
Kind of, yeah. This just stays in steady state. It's actually, the fact that many of you are shaking your heads as to how it works is kind of the answer. It's undefined. It can exist in any number of states. Does that make sense? If there's no potential field like driving the electron, there's nothing to define what the electron is doing. So the electron can exist in like any number of states, kind of in an undefined state. So we're going to get at that. How do you get that with the Schrodinger equation? This is the simplest example of the Schrodinger equation. All right. So from this boundary condition, you have to take this boundary condition to the one-dimensional steady-state Schrodinger equation. That's the simplest form of the Schrodinger equation that we just talked about. D squared psi dx squared is equal to 2m over Planck constant squared. The energy of the electron minus the potential V times the wave function psi. And what we're trying to do is solve for the wave function psi. So the first thing we do is we say V of x is equal to 0, so we just get rid of that term, and so you're left with this. D squared psi over dx squared is equal to 2m over h squared of E. Remember, E is the energy of the electron. That is the energy of the electron, and multiplied by psi of x. All right, so from here, what we do is, again, I'm trying to remind you of some tricks and techniques that is used that you may remember from your differential equations classes. If you don't, it's okay, right? So I'm just telling you that this is the method that's used to solve this differential equation. Once you know how to solve the differential equation, then it's just a matter of putting in boundary conditions. So if I tell you the solution is of a certain form, you can complete the solution even though you don't know how to get to the solution form. And I'll tell you what that means in a second. So this is a form of a differential equation where you have a second derivative and then you have the function itself. So the way that it's sometimes described in mathematics classes is they say that this is d squared minus k squared times the function. This part here is kind of, it's an operator. It's a differential operator that's sometimes used in differential equations courses. It's a shorthand. This capital D means the second derivative. And this k squared is, it's a known form. Well, what a known form is like someone who's good at differential equations would recognize that, oh, you know what? I've solved a differential equation like this before. It has a first derivative term and then it has something times the original function. That's a form that I recognize. It's like looking up an integral table, right? The integral of a certain function. If you don't remember it off the top of your head, you look it up in a table. If a differential equation has a certain form and it has a known solution. So what they do is they put it in this operator form, like d squared minus k squared, and this is the original function. And this k squared, in this particular case, this k squared is equal to 2me over h squared. So this is the k squared part of it. All right. So this k is part of the way that we're going to find the solution, and what the actual solution looks like is something like this. You have a second order differential equation. A second order differential equation is going to have more than one solution. So there's two functions here. And the best form solution is a sum of those two functions. All right. So when I said that there's a known form of the differential equation and you can get to the solution form, this is something that you could look up in a table. Okay, so you know that it's of this kind of form, and the solution to the differential equation is here. So the solution form tells you that, okay, this is what the structure of the function is going to look like, but I'm not completely done yet because I have to figure out something. So it says that psi of x is equal to some amplitude times the cosine function of kx, and this k is what I indicated earlier. And this k squared is equal to 2me over h squared. So the square root of k is equal to the square root of 2me over h squared. Right? So this is the form of the solution. So it's a sum of a cosine function and a sine function. The cosine function has this constant a1, and the sine function has this constant a2. So when I say this is a solution form, it's not the final solution because you still don't know what a1 and a2 are. You know everything else, but you don't know what a1 and a2 are. So does anyone remember how we solve for a1 and a2?
You find your boundary conditions.
You find the boundary conditions, exactly. So to solve a differential equation, you must have boundary conditions. All right, so in this case, there are no boundary conditions. Because we said, like, it's just the potential field is 0 everywhere. All right, so as a result of that, there's kind of two options. If the potential field is 0 everywhere, one possible solution is that the psi function could be 0. What's the physical meaning if the psi function is 0?
There's no electron there?
There's no electron. Good, very good. So that's not really a physical solution, right? So we know that there's an electron in free space. So there has to be a solution. What happens here is that, this was a solution form, and so our quote-unquote solution to the Schrodinger equation is just this equation without really defining these two constants. What this means is essentially that there's no boundary conditions to constrain A1, A2, and this K term here. So there's infinite numbers of solutions. And what that means physically is that an electron can exist at any energy state. Just one small detail here. This E, if you're wondering where this equation E came from, all we did was we took this relationship and solved this equation for E. So E is equal to h squared times k squared over 2m. The reason we solve for E is because, E represents the energy of the electron in a particular energy state. So this is telling you that the energy of the electron is equal to h squared times k squared divided by 2m. There's nothing constraining k. There's nothing constraining the wave number. So the electron could have any energy value, and it could the psi function could be any sum of those sinusoids, any possible sum of those sinusoids. So it's a simple problem, but it doesn't have a well-defined solution. All right, let's go to the next one, the 1D potential well. This is the second simplest example of the Schrodinger equation. And in this case, there will be solutions. There will be well-defined solutions to the equation, and it's going to look like a bunch of sinusoids like this. What we're going to do first is we're going to plug in this boundary condition. So the boundary condition here is you have this potential field, and the potential field is 0 when x is between 0 and L, and it's infinite when x is equal to 0 or L, or if it's greater than L and less than 0. Let me explain that a little bit better. A potential well, so this is x, this is the x coordinate. A potential well is where there's infinite potential here. So for all negative values, there's an infinite potential. And for all values greater than L, there's an infinite potential. So what this infinite potential does from a physical standpoint is that it constrains the electron. The electron sees basically the walls of a box. It's like taking the electron and putting it in a box. The electron cannot leave that box. All right? So the difference between the simplest problem and this one is that the first problem was free space. There's no walls. And in this problem, you've put an electron between two walls. Question?
Can that be considered as greater than L and less than 0, or just equal to 0?
Yeah.
You have infinity just for that add-on.
Yeah. Let me make a correction on there. So if x is less than or equal to 0, if it's greater than or equal to L, then it'll be infinite. Actually, I think the easier way to define this, sorry, I'm making some changes here, but it says x is less than 0, x is greater than L, and this will make this equal to, less than or equal to.
But at that point, your box doesn't really exist, so, right?
Just a sec, just one second. Okay, sorry, go ahead.
At that point, what was the point of making a box?
At that
point, the box really doesn't exist, right? If you go above the outside of those bounds, then what's the point of the box?
Yeah, if you go outside of the those bounds, the potential is infinite. So basically the infinite potential doesn't allow the electron to escape. The electron is constrained in a space that has a specific length L. That's the way that you can think about this. All right. And the reason we do this problem, first time I saw this, I'm like, why? This seems like a really arbitrary situation. Why do you do this? Well, part of the reason we do it is because there's a simple solution to the Schrodinger equation that illustrates how the Schrodinger equation works. All right, so we plug that into the Schrodinger equation, and I'm actually going to go through the steps with you. Just ignore this here. We'll get to that solution. So you start off with this boundary condition, okay? So this boundary condition is v of x is equal to 0 for 0 is less than x is less than L, and it's infinite at infinite out here and out here. So the first step in solving the Schrodinger equation is just like before. This is going to look familiar. So we had this the one-dimensional steady-state Schrodinger equation, and since the potential in the well is 0, v of x is equal to 0 inside the well. We're solving the Schrodinger equation inside the well. That's why it's equal to 0 there. So we can basically cancel that out just like last time, and we're left with the exact same equation as before. And so the solution is also the same as before. Right? The solution is a sum of cosine and sine. Cosine of kx, sine of kx. This k is equal to the square root of 2me over h squared. The difference in this problem is that there is a boundary condition. The boundary condition states that psi of 0 is equal to 0 and psi of L is equal to 0. Okay, so that's why I want to specify this specific detail here. Okay, it's 0 here, but once you get beyond this, then it's infinite. So at x equals 0, the potential is 0, and at x equals L, the potential is 0. Once you go beyond that, then the potential is infinite. Okay? All right, so from there, when you want to solve it, the solutions to the Schrodinger equation is a set of sinusoids, and each one of these sinusoids has a specific quantum number n. So I want to get into why that's the case here. Let's see, I don't think I have this in the notes, so it might be good to just write this down separately. Okay, I'll do this in one note. All right. Okay, so we have this function a1 sine of kx plus a2 cosine of kx So this is your solution form. All right, and the boundary condition you have psi of 0 is equal to psi of L, and this is equal to 0. All right, so this is what, if we draw the system out here again. So this is x equals L. And what we're going to draw here is we are going to draw the psi function. Yep, thank you. So psi of x. Okay. All right, so this is x equals L, and this is x equals 0. Okay, so we have the form of the solution, and now we just need to plug in the boundary conditions to figure out what A1 and A2 are. So let's first plug in, let's see what we can do with psi of 0 equals 0. All right, so this is the first boundary condition. We have two boundary conditions and we have two unknowns, so that will allow us to find A1 and A2. So we plug in 0 equals A1 sine of k times 0 plus A2 cosine of k times 0. So this term goes away, that's 0, and cosine of 0 is equal to 1, so 0 is equal to A2. All right, so now our equation just simplified, because we know A2 is equal to 0, so let's just get rid of that. So now the form of our solution is just psi of x is equal to A1 times sine of kx. So now we're going to look at our second boundary condition. Psi of L equals 0. All right, so 0 is equal to A1 times sine of kx. All right.
It's going to be L, X.
Oh, yeah, thank you. Yep, thank you for that. All right, sine of k times L. All right, now what do we do here?
I mean, even if we multiply with sine inverse on both the sides, we still won't get that A1 value, right?
Yeah, so one suggestion was to solve this equation. We want to solve for A1, right? Or we want to find a working solution to this system, right? One possibility was just doing the inverse sine of both. And yeah, that's not really going to help us out, right?
So it even, yeah. Good.
So this is where, yeah, go ahead.
Keep an assumption like if L equal to this value, this is A A1 is going to be this value, if L equal,
So I think whatever value you consider for L, it's going to be ultimately be 0 because there itself we have the boundary condition that whatever the L, psi of L is 0, right?
Yeah, we need to somehow get psi of L, psi of, we need this condition to be true, okay? Because we're constraining this condition. All right, and this is where, how many of you have seen eigenfunctions and eigennumbers before? You have. Okay, so this might look familiar to you. For those of you who haven't, it's okay. So we're gonna do a little crash course on it right now. So in order to solve this equation, our A1, either A1 has to be 0, either this has to be 0. If that's 0, that can't be the case, right? Because if A1 is 0 and A2 is 0, then we basically end up with a solution psi is equal to 0. That means there's no electron. Bad solution. All right, so that cannot equal to 0. So this has to equal 0. This term has to equal to 0. This has to equal 0. Oops, 0. So sine of KL equals 0.
Could be sine 0, right? I mean, if 0 is or anyway sine 0, so if we can equate the angle of both of them, so then KL will be equal to 0.
or pi.
Or pi, yeah, there you go. So, okay, sine of KL has to be equal to 0. Okay, now let's look more closely at this. So, okay, one possibility is that K is equal to 0. Okay? What does K represent physically?
Wave number.
Wave number. So if we have a wave number of 0, what does that represent?
No way.
Nothing.
No wave. It's like a wave with 0 energy. Is that a physical solution? No. All right. So that's not going to work. Just trying different things so you can see how the mathematicians thought about this earlier. But the sine wave has this unique property. It goes like this, right? There are many places in a sine wave where it's equal to 0. Where are the places where sine is equal to 0? There's two possible. Well, actually, there's infinite possibilities. Yeah, exactly. So sine of let's just say sine of y equals 0 when when y is equal to 0, when y is equal to pi, when it's equal to 2 pi, 3 pi, 4 pi, and so on. Yeah, it just goes on and on and on and on. All right? This is the key intuition. Like when people start talking about differential equations and eigenfunctions and eigennumbers, you'll know this is exactly what they're talking about. So in order for sine of KL to be 0, so let me just erase this. This can be 0 if KL is equal to 0, or if it's equal to pi, or 2 pi, 3 pi, all these possibilities, right? So sine of KL is equal to 0 if KL is equal to 0, pi, 2 pi, 3 pi, and so on. So a mathematical way of saying this is that KL is equal to n times pi, where n equals 1, 2, 3, 4. Yeah, 0, I actually don't include 0 because 0 is a non-physical, it's a non-physical solution. That would be a wave number of 0, so that's why we don't include 0. But good, that means you're all listening. So what I'm going to do is I'm just going to take this one out, right? Because 0, yes, it would work if it was 0, but that's a non-physical solution. So just in terms of terminology, these are eigennumbers. And the corresponding functions that are solutions to that are called eigenfunctions. All right. Let me do this. And move this down. All right. So now, let's figure out what the functions are. So the possible solutions to this function, psi of x is equal to a1 right, we still have a1. Don't forget a1 because we didn't say if a1 is not 0, so it's equal to something else. So a1 sine of KL where KL equals, kx, my bad. We're talking about the original function again. So kx, where now we solve for k here. So I said KL is equal to n pi. So k is equal to n pi over L. So where k is equal to n times pi over L. And n equals 1, 2, 3, 4, and so on. So this set of functions, the first function might look like this. A1 is sine of pi over L times x. All right. If we were to graph that function, this is, by the way, this is for n equals 1. This is where n equals 1, the first function. So psi 1 of x is equal to a1 times sine of pi over L times x. What is the wavelength of this function?
Is it L over I?
So if we want to find the wavelength of the function, we take this. And so the wavelength is, this is the wave number, k.
2 pi over k.
This is 2 pi over k. So this is 2 pi over L, which is equal to 2L. All right? So what if you were to graph this function, we'll do these in different colors. So the first function would look something like this. All right, this is psi 1 of x. So this is in blue color. All right, does everyone see this here? So intuition here, remember our boundary conditions. Our boundary conditions were that here, let's see, I'll do this in green so it's not confusing. Boundary conditions. Notice that psi of x is equal to 0 at x equals 0 and x equals L. Right? It's a sinusoid, but it's 0 at both boundaries. Right? Okay. Now let's do psi 2 of x is equal to a1 times sine of 2 pi x over L. All right, so the wavelength here is equal to L. So what this sine function looks like, let's see, if we split this in two, this sine function is going to look like this. All right, it's also a sinusoid, but guess what? At x equals 0 and x equals L, it's equal to 0, right? So this is psi 2. Now, psi 3 of x is equal to a1 sine of 3 pi x over L. And so the wavelength here is equal to, what is it? So 2 pi over 3 pi over L. Okay, what does that come out to?
2L over 3.
I'm sorry?
2L over 3.
2L over 3. So it's 2/3 L is the wavelength. All right, and that one I believe looks something like, yeah, it looks something like this here. Let's see, we divide this into 3 parts. 1, 2, 3. So it goes up like this, down, up like this, down. It's still 0 at x equals 0 and x equals L. So do you see how there's an infinite number of sinusoids you could have that would solve this constraint?
But the function also becomes 0 in between 0 and L, right?
It does. But our boundary conditions didn't say anything about what happens in the middle. It only said something about what the boundary, what the constraints are on the two edges, x equals 0 and x equals L. So with partial differential equations, you have to specify these boundary conditions in order for the Schrodinger equation to be solved. Now, the last step here is how do you find A? And I'm just going to go over that real quick. So how do we find A1? There's another equation that you can take into account in order to find A1. And that equation is something that we talked about earlier. It's the condition, that the probability that the electron exists over the entire space is equal to 1. Okay, so in this condition, in this particular case, our domain, here, let me just write this down. Integral of psi squared dx from x equals negative infinity to infinity has to be equal to 1, right? So our domain, this is a one-dimensional Schrodinger wave equation. Our domain is, is domain all possible values of x. And we look at this function psi squared. All right, so this is going to come out to something like this. We have to do the integral from, let's see, x equals 0 to x equals L of psi squared. So psi squared is going to be A1 times sine of n pi x over L. This whole thing squared. Let's see, that's dx equal to 1. Now, so a couple things here. First of all, notice that this 0 and L here. All right, the electron doesn't exist. There's zero probability of finding the electron outside the box because it's infinite potential outside the box, and electrons cannot exist at infinite potential. So it exists in that potential well in the middle there. So that's why we changed this from negative infinity to infinity of just to just 0 to L. This is where our wave function is defined. All right, and we're taking the absolute value of that wave function and we're squaring it. All right, this particular wave function did not have any complex conjugates, so all we did was took the magnitude of it and squared it. This was not a complex valued function. This was an entirely real valued function. So from here, I think in order to save time, we probably don't want to get into this part here. But the way that you solve this is, sine squared of x. The way that you solve the integral of sine squared of x is that you use this identity, sine, what is it? Sine of sine squared of x is equal to 1/2 1 minus cosine of 2x. All right, and using this identity, you can find the integral of this equation, and basically when you solve it, it comes out to a1 is equal to the square root of 2 over L. The square root of 2 over L. All right? So our solution then becomes psi of x is equal to the square root of 2 over L sine of n pi x over L. Make sure I got all that right. No. Yeah. Sine of n pi x over L. where n is equal to 1, 2, 3, 4. So we can say psi n of x. So this is the solution, and you can see that the solution is not one function, it's a whole set of functions. So that's what these are referred to as eigenfunctions. So these are the eigennumbers, n equals 1, 2, 3, 4, 5, those are the eigennumbers, and each number has a corresponding eigenfunction. And they're all solutions to this equation, because they can all, as you can see, all these sinusoids can, it solves the differential equation and also meets the boundary conditions. So when you have all these conditions, what does that physically mean? What does it mean when there's multiple wave functions that can meet your constraints?
There's no specific proposition.
Close. It's not like the first one. The first situation was that there was the k could take on any value. In this case, k can only take on certain values. So what does that mean?
Potential is randomly distributed in those two groups.
Not randomly. That's the interesting thing. I see where y'all are getting at.
That n values.
What's that?
At the point where we have the n.
Yes. Yes. The fact that you only have specific solutions, you have a whole bunch of solutions, but they're of a specific form. That means that electrons can only exist in certain wave functions that have certain frequencies, certain wave numbers associated with them. There's a high wave number one, there's a lower wave number one, there's any number of them, but they're discrete. This is the key concept. They're discrete. They're discrete energy states that the electron can reside in. You remember with the Bohr model how, one of the key outcomes of the Bohr model is that Bohr said, electrons can only exist in discrete energy states, not any random energy. They can only exist in discrete energy states. Schrodinger's equation is saying the same thing here. But it's just giving us a lot more information about the electron than the planetary Bohr model. And this is the more correct model. So the solution is a set of eigenfunctions. It's a set of functions that we just talked about, and this is the form here. And each of these functions corresponds to a certain energy state, a certain wave number. Each wave number has a certain energy state associated with it. And the energy state of each wave number is given by this equation. How did we find this? It's quite simple. Sine of n pi x over L, the solution that we had, the solution of our differential equation was in this form, sine of k times x. And the way that we denoted this k was related to the wave number of the electron. That's how we defined it earlier. So this k is equal to the square root of 2m times e divided by h squared. So if we solve this for e, then we get e is equal to n squared times pi squared times h squared over 2ml squared. Notice that the n comes in here too, because our k is equal to n pi over L. So k is equal to n pi over L. So now the physical explanation here is that we have all these different energy states. E sub n is equal to this equation here. But n can only exist in n equals 1, n equals 2, n equals 3, and n equals 4. So there's a bunch of energy states, E1, E2, E3, E4. Those are called the eigenenergies. And for each eigenenergy, you have an associated wave function, which is a sinusoid. So higher energy wave functions have a higher frequency, have a higher wave number. They have a shorter wavelength. Yeah, I should not say frequency. My mind always just goes to frequency, but I should just say higher energy means shorter wavelength. Okay, because that corresponds to de Broglie's thesis, right? De Broglie said like higher energy, higher velocity corresponds to smaller wavelength. All right. If you don't mind, I just want to say 5 minutes extra, and we'll just touch on a few more things because we started a little bit late. I just want to finish up with this concept. All right, so we went over this. The physical meaning is that each solution corresponds to an energy state which can be occupied by an electron. Higher frequency solutions, I should say shorter wavelength solutions. shorter wavelength. Shorter wavelength solutions, you could also say higher wave number. Higher wave number solutions corresponds to higher energy states. In multiple solutions means there's multiple ways an electron can exist. So each state, this is where we're getting into the question of where is the electron located. All right. So in this problem, we said, okay, the electron is in a box. It can't be outside the box. It's somewhere in the box. But where in the box is it? So when you take this psi function, if you want to find where the probability of finding an electron is, remember you have to square that psi function. So when you square the psi function, you get something that looks like this. So for example, this psi 2 here, the one that in the blue line, that was one of the solutions of the Schrodinger equation. Notice that it goes positive here and it goes negative. But when you take a function and you square it, it just becomes positive, right? It's all positive. So that's why the function looks like 2 humps on top when you square the function. All right, so this is telling us that the psi squared, which is telling us the probability of finding an electron, this is the probability density function. It's large at L equals 4 and it's large at 3L equals 4. So this happens to be the region. The electron is highly likely to be at L over 4 and 3L over 4. What's wild and weird is that in this energy state, the electron is not likely to be in the middle. So this gets back to, I think, Sri, your question earlier. You were saying, well, the wave function is 0 in the middle. How could that be? The electrons can actually exist. In this solution of the Schrodinger equation, the electrons exist at L equals 4 and near 3L equals 4, but not in the middle. In the lower energy equation, in the lower energy solution, it's psi 1. If the electron is in that energy state, then there's a high probability of it being in the middle. Okay, but what you notice among all the solutions of the Schrodinger equation is that the probability is always 0 by the time you get to x equals 0 and by the time you get to x equals L. So it's physically meaning it has a physical meaning. The electron cannot exist at the highest at the infinite potential regions. All right. Now, what I'm going to quickly do in the next 5 minutes, and it shouldn't take long because this is just an overview. I'm not going to go into any derivations for this one, but we spent a lot of time looking at the derivations of the one-dimensional case so you can understand how the process works. But in the three-dimensional case, it's not easy to derive the solution to the Schrodinger equation. The solution of the Schrodinger equation in this case is going to have three, it's going to have 3 dimensions. But the process is similar, even though it's more complicated. The basic process is the same. You take a boundary condition and you plug it into the 3-dimensional Schrodinger equation. The difference is that in this case, the boundary condition, the voltage, okay, the potential field is equal to q squared over 4 pi epsilon r. The reason for this is that you have a nucleus in the middle that's packed with protons. And as I said at the beginning of class, that nucleus is going to have a high potential, right? Because there's a lot of positive charge there. Wherever you have a lot of positive charge, there's high potential. Wherever you have a lot of packed electrons, there's negative potential. All right. So with this electron, there's a lot of a positively charged nucleus. There's a high potential field close to it. As you go away, as you increase r is the radius, the distance away from the nucleus. As you go farther away, it drops off. That's what that 1 over r function is. So 1 over x, it drops off like this. Right? So the farther you go, the potential drops to 0 as r goes to infinity. So that is your v in the Schrodinger equation. So here we solved the one-dimensional Schrodinger equation. You know how we had a v here that we had to put in? This is a 3-dimensional equation, and now we have a 3-dimensional electrostatic potential field. We plug that into the Schrodinger equation, and the result that we get looks like this. So So these are three-dimensional wave functions. And, before we plotted out like one-dimensional sinusoids, right? These are, in your homework, you're going to have some plotting out two-dimensional sinusoids. These are three-dimensional sinusoidal functions, okay? So what's intuitive here, what you want to think about is that one of the trends that we noticed from before is that higher energy electrons have higher frequencies associated with it. And what that means in terms of in terms of three dimensions is that you notice that there's many more lobes here. They call these things, they call each one of these solutions, they call them orbitals. Okay? And the higher energy orbitals, they have more lobes associated with them. Like more little lumps coming out of there. So these are all the different states that an electron can reside in. Okay, the lowest energy solution of the Schrodinger equation looks like a sphere, and then the higher energy ones at n equals 2, these ones start to look like dumbbells, and then they just start to get more and more complicated. Some toroidal shapes, some like mushroom shapes. It just gets like really crazy, especially you get to the higher energy states. All right, but these were solved in the same way. You're taking a partial differential equation, you're plugging in a boundary condition, and you're finding the solution to that boundary condition. And then where the orbitals are is where the psi squared, where the probability is high, that's where they draw these orbitals. So just like before here, when we drew out, we said, hey, there's a high probability of finding the electron at L equals 4 and 3L equals 4. So we're going to shade those regions yellow and say those are the locations where the electrons are most likely to exist. So if we had to draw shapes indicating the shape of an orbital, that's what they'd look like. This is in one dimension. But in three dimensions, they start looking some crazy stuff like this. Okay. I was hoping to finish up this chapter today, but I think we'll just do that. We'll do that quickly on Monday. So we're going to talk about electronic configurations. And you should be able to do all the questions in your homework at this point, except for the last question, and it's an easy question. You'll see it. It's just filling out electron states in an energy level diagram. So we'll finish this up on Monday. If you have questions about the homework, please let me know. Please feel free to email me. I'll be here after class today if you want to ask me anything, and we'll kind of go from there. Thanks for your attention, and sorry that we ran 10 minutes late today. I appreciate the extra time.